next problem is kind of more restricted than the previous one. We have to find the duplicate number. We are given an integer array of integer called nums, and it contains n plus 1 integers, where each integer is in the range 1n inclusive, 1 to n inclusive. There's only one repeated number in nums. We have to return this repeated number, and we have to solve the problem without modifying the array's nums. So the negative mask or adding the length of the array or any kind of operation on the input array is not allowed. And we also have to use only constant space, so we cannot create a hash map or a hash set or anything else. So it's definitely more complicated than the last one. Now, from the examples, as you can see, we have 2 and 2, which is a duplicate number, so we just return 2. And the next example, we have 3 and 3, and so we return the number 3. From the constraints, the length of the array ranges from 1 to the 10 to the 5th. And as we can see, the numbers are appearing from in the range 1 to n plus 1, which is your first kind of like, it's kind of sketchy, like 1 to n plus 1, because if you reduce 1 from this, it will go to 0 to n. And so that's kind of interesting. Maybe we can use this somehow. So all the integers nums appear only once except for the precisely one integer, which appears 2 or more times. And then we have a follow-up. How can we prove that at least one duplicate number must exist in nums? And can you solve the problem in our time complexity? So first thing here is that if we cannot use any additional data structure, we could sort the array. And if we sort the array, it would look, for example, this one, it would look like this. 1, 2, 2, and then 3, 4. Then we would just traverse and see that the neighboring elements are the same. So we would just return 2. But we will get n log n time complexity. And we have to solve it. We have to try to reduce the time complexity to linear. So it's definitely more restricted. Problem statement, we have numbers ranging from 1 to n, and the array length is n plus 1. We know that we will have valid indices for each element. So we will be able to map every element to some indice. And we will also always use our function, just decrementing by 1 to find the corresponding index. So let's look at an example. Let's say we have an example 3, 1, 3, 4, 2, which is an example from our problem statement. And let's say, how can we create a linked list from this input array? And to create a linked list, we have to define the next operation. So we have to find how can we map this next pointer. So if we start with our first number and put it as our first node in the linked list, we can use the index that this number is corresponding to as our next value. So we can say that 3 is pointing to the number that's at the index 3. So in this case, it will be number 4. And then we can move to number 4. So let's say number 4 is pointing to the element that's at number 2. That's at the index 4. In this case, it's the number 2. And then we have the element 2, which is pointing to the element that's at index 2, which is 3. And then again, we have 3, which is pointing to the element which is at the index 3, which is 4. And as you can see, we get this cycle in a linked list. And if you have a cycle, you know that there are multiple elements that are pointing to the same node. In this case, we have this element and this element pointing to the same node 4. But as you can see, they are the same elements. They are duplicates. This index, this strategy of using index as our next operator in the linked list is enough to find a duplicate number. Because as you can see, the number 3 is pointing to 4, But later in the array, later in the linked list, we have again number 3 that's pointing back to the 4. So we will have 2 elements in the array that are pointing to the same node. And this is basically our entry point to the cycle. And we just have to find the entry pointer to the cycle, and we found our duplicate then. And to find the entry point to the cycle, we will use an algorithm called tortoise and hare, or Floyd algorithm. And it basically uses 2 pointers, slow and fast. The fast is moving twice the speed, and slow is just moving one step at a time. So if we put the slow at our first element and the fast to our second, you can just imagine that there is an imaginary node, and slow moved 1 step to this, and fast moved 2 steps to here. So that's our initial configuration. Now we know that slow will move only one place at a time. I will put slow here, so it's currently here. In the next iteration, it will move to here. And we will also have fast, which is now here, but in the next iteration, it will jump from here to here. So it will point to here. Next, slow will move to number 2, to the node with the value 2. And our fast, which is currently here, will move again to the 4 and then back to the 2. So they met. They met at this point. We have our meeting point. Now, how can we use meeting point to find the entry point? Well, let's just quickly reset the canvas so we have more space. Let's say this is our entry point to the cycle, and we have a huge cycle. And let's say this is where they met. So this is our meeting point. Let's call this distance from the head of the linked list to the entry point, and let's mark it as x. Also, let's mark the whole cycle length as c. So c is the cycle length. It can be few nodes in the linked list, whatever. Now, we also have the meeting point. So let's say that meeting point, so the distance from the entry point to the meeting point, let's just call it a. So a is the distance between entry point to the cycle and our meeting point. So how can we find the entry point? Now, first, we know, let's just declare d fast as the speed of the, basically the length of the number of nodes that the fast pointer has traversed through. And let's say that we have so it's the distance that our pointer has gone through. The slow is basically the same. Now we have this relationship. We know that our fast pointer is 2 times our slow pointer. And we know at meeting point that they cross the same distance. At the meeting point, they basically went through the same distance. And so we know that d slow is the distance from the head of the linked list to the entry point plus the distance from entry point to the meeting point, which is a. Now for our fast pointer, we will have the distance from the head of the linked list to the entry point, the number of cycles that that the fast pointer went through. It can be 1, 2, whatever, depending on the speed of the pointer, and then also the A, which is basically the distance from the entry point to the meeting point. Now we know that we can use these three equation to say that so we basically replace fast with this, and we know that x plus nc plus a is equal 2 times d slow, which we can exchange with this. So that leads us to nc being equal to x plus a. So one cycle in the, or multiple cycles in the length of cycles is equal to the distance from the entry, the head of the list to the entry point, and the distance, added up distance from the entry point to the meeting point. So if we put r, and we know that that they met here, so the fast pointer needs to go only x points, x linked list nodes, and if we put it to finish a circle, we finish the cycle, and slow, if we put it at the end of the list, at the beginning of the list, has to move x linked list nodes to end up here. So if we put the slow at the beginning of the linked list and keep our fast at the fast pointer at the current position and move them step by step, they will, after x linked list nodes, they will meet at the entry point, and that's basically that's our duplicate number. That's the entry point that we had from the example before. So we will use this to find the entry point to the linked list cycle, which is also the duplicate in the input array. We will solve the problem using Java programming language. We will first declare slow to point at the first number, and fast, because it's moving twice the speed, will point to the number the first number is pointing to. Kind of tricky to say. Then we will iterate over, moving the fast twice the speed as the slow pointer, and each time we will use the index as our next as a way to calculate the next node. And for example, we have slow, which is currently pointing at one element, and to move it to the next node, we will just use it as an index, so it will be num slow. And for fast, we will just have the double speed, so it will be nums and then whatever we got from the nums fast. And the loop will go on and on until they meet at a certain point, which we call meeting point. Then we will place slow at the beginning of the linked list, and which is in this case is just 0. And by the problem's constraints, we know that we will never have 0 because in the SN element in the input array, so we will not have an infinite cycle inside the element 0, because the range of the elements that we have in the input array are ranging from 1 to n. Now we will declare it then at the position 0, and then fast remains at the position that it's at, and we will move them step by step until they meet again. And when they meet, by the formula that we already explained, they will meet at the entry point to the cycle. And that entry point is also the duplicate that we are searching for. The time complexity for this solution is only traversing through the array, and that's basically linear, and it's proportional to the length of the array, while we don't declare any helper data structure. So that means that we have a constant space complexity.